SwayamPrabha. Digital India. Educated India.
Hello, we are going to now start a new module or chapter, energy and energy transfer. But before we go into details, let me just summarize what we have gone through quickly in last 3 lectures. So we started with the importance of thermodynamics in various application areas in daily life, and defined the SI units and the importance of homogeneity of dimension, which essentially means A is equal to B plus C. A, B, C should have all similar units. We define the systems, control volume, property of a system, and something like density, specific gravity. The more important thing we went through was state, definition of state, and the state postulate, which relates how you define a specific state based on intensive variables. We talked about processes and cycles and what is a steady state process. And then we went through the introduction of temperature, the pressure definition, and as well as how to measure. And then we ended with the importance of a problem solving techniques. So in this we are going to learn about the concept of energy. We'll define different forms of energy. We'll discuss the nature of internal energy. We'll define the concept of heat and the association with energy transfer by heat. And then in the next lecture we'll talk about work. So let us just understand a bit of energy conversion or conservation, and as well as conversion to different form. So let's take an example of this. This is a refrigerator which you have opened the door in a room, okay, and then what you have done is you have well sealed and insulated the room. So what you have is a system which contains air plus this device, which is refrigerator, and the boundary of course is your walls of the room, and then you have this interaction with the surrounding through this electrical point. Now the first thing you will think that the room will get colder, but it's not the case. Later on you will realize that it's going to heat up, and the reason being is conservation of energy. You are transferring electrical energy into thermal energy, okay, because the electrical energy is provided by this, and then you are increasing the temperature of the room by conversion of electrical to thermal. Okay. So there are many forms of energy. Thermal energy I said once already. Thermal is one. Mechanical, kinetics, potential, electrical, magnetic, chemical, and nuclear. Some are macroscopic in nature, which depends on the elevation of the overall system velocity. Some depends on the molecular motions, which is macroscopic. So the macroscopics are kinetic and potential, and macroscopic ones are which are related to molecular structure, which is independent of outside reference. We are going to discuss about this more in detail. It's basically internal energy. Now if you are defining the energy of the total system, then you have to consider the macroscopic and microscopic both together. So total sum of all form of energy will comprise the total energy, okay. On the other hand, sum of all macroscopic form of energy will be called internal energy. Okay, let me first go through the macroscopic forms of energy first, and then I will talk about the internal energy. So as we already discussed, the macroscopic forms of energy depends on the elevation and the speed of the system or the object. So this is the classic examples are kinetic energy, which is represented by this expression, which is mv square by 2, and the potential energy which is represented by mgh, where z is the elevation of the object. You can define in terms of per unit mass in this form. You divide by the m, you get this v square by 2, okay. So the macroscopic forms of energy is simply related to motion and influenced by the external field. So that could be not just gravity when we talk about elevation, but could be magnetic, could be electricity, could be surface tension, okay. So if the magnetic, electrical and surface tension forces or external field are absent, then the total energy of the system would be the internal energy, which is a macroscopic, plus the macroscopic one, which is kinetic energy and potential energy. Okay, so this is the expression which you're going to write. Okay, so let's look at internal energy. So internal energy can be divided into many forms. Rather, it comprises of many aspects of these energies. So one is sensible energy. So sensible energy is simply associated with the kinetic energy of the molecule. So what is the kinetic energy of the molecule? So molecule can vibrate, okay, can rotate, okay, and can translate. Okay. Additionally, the molecule consists of nucleus, electron. Electron can rotate around the nucleus. Electron can spin around its own axis. Nuclei can also spin around its own axis. So this comprises sensible part of the internal energy, and that's what it's written in this illustration. So this is all sensible part of the internal energy. In addition, the energy required to change the phase of the system is also part of the internal energy. So that would be a latent energy. So examples would be when you change liquid water to vapor, when you melt solid ice to liquid. These are all the energy required to change the phase would be latent energy, and this is also part of the internal energy. In addition, the molecules during the reaction, the molecules are they break bonds and turn to different species. That is a chemical energy, because that is associated with the bonds. Okay, that will be chemical energy. And then you have this nuclear energy, where the energy is associated with the strong bonds within the nucleus of the atom, and this is extremely large amount of energy. So in this, we are not going to consider nuclear energy as a part of the analysis, but these are all part of your internal energy. So typically thermal energy would be a sensible energy plus latent energy. So we will talk about thermal energy. It would be sensible energy, because that is what the energy associated with the movement of the molecule, plus if there is a phase change. And internal energy would be sum of all this energy which we have listed. Okay. Now the system, when you put it in place in a container, let's say water in a container, there is energy stored in the system. That is called a static, because there is the movement with the boundary. But there are other energies which is associated with the transfer of energy from the boundary to the system, and these are called dynamical form. So the one is a static form, the other is dynamical form. So the dynamical forms are the ones which are associated with energy gained or lost by the system during the process. It is only recognized only when it gets out of the system or comes to the system from the surrounding. And heat transfer is one example. Okay. So the two forms of the energy associated with a closed system, which means the mass is not flowing, will be heat transfer and work. If there is a temperature difference, let's say in surrounding and system, it will be heat transfer. Otherwise, it will be work. Okay. So this is an example of dynamical form, and we'll try to illustrate this more, get into more depth of that. So we talked about macroscopic kinetic energy. What is a macroscopic kinetic energy? When you have a fluid, let's say, and it moves with or the object which moves with a velocity. Now, and then you have a macroscopic kinetic energy, which is a part of the sensible energy, where the molecules are moving. Now, these molecules, they move in a disordered form. Now, this is an illustration which tells you that a macroscopic kinetic energy is more organized and more useful than microscopic kinetic energy. And for example, you put a water, and this is a dam, this is a turbine wheel, and if the water doesn't flow, the turbine wheel will not rotate, even though the molecules do move a lot. On the other hand, if it flows, you have a perfect, the energy can be generated later on. So essentially, it tells you that macroscopic kinetic energy is more useful than disordered microscopic kinetic energy. Okay, there are many engineering systems which are designed to transport fluid from one location to another at a specified velocity, flow velocity, or certain elevation. Now these do not involve any conversion of chemical or nuclear energy to mechanical energy, but it can be analyzed by considering the mechanical form of energy. So let's look at it. What is a mechanical form of energy? This is a form of energy that can be converted to mechanical work completely and directly by an ideal mechanical device such as ideal turbine. The examples are kinetic energy and potential energy, macroscopic kinetic energy and potential energy. And thermal energy is not a part of mechanical energy. The reason being that thermal energy cannot be converted directly to work completely. Okay, and due to second law of thermodynamics, and that's something which we are going to learn later. Okay, So let's take an example of pump. Pump transfers mechanical energy to a fluid and it raises its pressure. Turbine extract mechanical energy from the fluid and by reducing its pressure. Thus, the pressure of a flowing fluid is associated with mechanical energy. Okay. The pressure, though is not an energy, but when the pressure force acting on the fluid through a distance, it produces a certain work. Okay, and this work is called flow work. For the convenience, we say as flow energy, and we include that as a part of the mechanical energy. So overall, we can define mechanical energy in this form. So mechanical energy per unit mass includes flow energy, which is nothing but flow work, and plus kinetic energy plus potential energy. Okay, so this is nothing but PV, which can be written also as P by rho, and this is your kinetic energy, and this is that. In terms of rate, we can write in this form. So you can find out the change in the mechanical energy for incompressible fluid. It will be simply a difference in pressure and the difference in kinetic energy and difference in elevation. So in case of a system which do not have any change in the pressure or difference in velocity, or is particularly static at elevation is not changing, in such case your delta E mech is going to be 0. Now for the case where the mechanical energy is transferred to the system, your delta E should increase. If your for the case where it is extracted from the system, your delta E mech should be less than 0. So this is the case for transfer from the surrounding or to the system. That means the fluid, the mechanical energy is being transferred to the fluid, hence your change in mechanical energy should be greater than 0. Okay, and this would be the case where you have extracted mechanical energy from the system, such as your turbine. Okay, so we can take an example and apply this aspect. Now in case of an ideal hydraulic turbine, what would be the maximum power? So assuming that this is a case where you have ideal hydraulic turbine connected with ideal generator, and it means there is no loss of energy anywhere. So whatever the mechanical energy of the fluid is transferred to the work done by the generator. So this is a maximum power. Okay, will be simply m dot E delta E mech. Now what we are assuming that, so there are two cases we are going to consider. One is here where we are considering this 1 of 4 point, which are this is upstream and this is downstream. Okay, so the pressure here we are going to assume to be same, that the elevations are not, the difference is not so much, there will be a change in the pressure, so it will be almost close to atmospheric pressure. Now what about the velocity? Both the reservoir which we are going to use will be not flowing, so we are going to consider them to be at stationary, which means the V1 should be same as V4. So in that case your delta E mech should be simply the change in the elevation, m dot G delta Z. Okay, and hence it is simply change in the elevation of the two reservoir. Now you can zoom this and you can also express this maximum ideal power in terms of the pressure drop across the device, that is turbine, and this is the second case. Here you apply the same expression, but now you are considering these 2 points, 2 and 3. Okay, now here the velocity we are going to consider almost close same, that means the velocity is not changing much. Elevation we are considering to be almost similar. This is because the scale, if you viewpoint of the scale, the change in this Z is small compared to what we have shown in here is in the difference between the reservoir heights. So this will be simply written as the change in the pressure across the turbine, because the rest of the component is going to be 0. So this is the application of your mechanical energy. Now as I mentioned already that there are two forms of dynamical energy. So system contains a static energy and system can undergo a dynamical change, but those will be recognized only at the interface. So for a closed system, you have two possibilities, that is heat when there is a change in the temperature, and there is a work. And heat is the one which is a form of energy that is transferred by the virtue of temperature difference, okay, between the two system, or it could be system and surrounding. So we'll talk about heat first, and then we'll discuss about work later. So let's take an example here. So you have a room temperature at 225 degrees Celsius. You put a soda or can of soda which is also at 25 degrees Celsius. What is the heat transfer? It will be 0, because this will be at equilibrium with the surrounding. You take the same can from a refrigerator at 15 degrees Celsius, the temperature difference has increased, which allows the heat to transfer. It is 8 joules per second. You decrease this temperature of this can, or increase the temperature difference, you increase the heat transfer. So this tells you that the temperature difference is the driving force for heat transfer. The larger the temperature difference, the higher is the rate of heat transfer. So we'll consider a couple of more examples here. So let's take an example of a baked potato. So the baked potato, if it is isolated, is not going to transfer any heat to the surrounding. But if you take out from an oven, you're going to notice that it will slowly cool down. But it doesn't cool down directly, like it has a step, because it contains, when you take out, it contains the thermal energy of very high temperature, base thermal energy. And then it transfers to the surrounding in the form of heat. But this heat which you see here is only at that boundary. Once it transfers to the air, the amount of energy gets a part of transfer to the part of the air. So the air thermal energy increases. Okay, you don't feel the temperature rise because of the white, the room and so forth, but you can always see the differential change when you take out the potato close to your body. So energy is recognized as a heat transfer only as it crosses the system boundary. So I've said this many times, just to emphasize. If you put an insulation around a system, you will make system to be adiabatic, which essentially means there is no transfer of the heat. That is, we're going to use Q as a representation of heat. So the Q is going to be 0 here. Okay. So it's also used as small q, but that is only on the basis of unit mass. So that will be unit is going to be kilojoules per kg. And if it is a rate of heat transfer, then we are going to use Q dot. And in such case, you can integrate the amount of heat. So if you want to find out the total heat transfer between T1 and T2, you just have to integrate Q dot over the time. Okay. All right. So let me end this lecture with this background of heat. Now, in early 19th century, the heat was considered as a massless, odorless, tasteless object, or some material or object, substance, which transfer from a hot body to a cold body. It was until the theory or kinetic theory was developed, this was the notion. Okay, of course it was wrong, it was incorrect, but that caloric theory brought a lot of understanding of the heat for us. So what kinetic theory tells us is that this heat is nothing but is the motion of the molecules, and kinetic theory relates the kinetic energy to the temperature. Okay, what does it mean? That a hot body like hot water or steam should have higher kinetic energy of the molecules compared to something which is a room temperature. Okay, so heat is nothing but the energy association with the random motion of atoms and molecules. Okay, so it is typically done through conduction, convection, and radiation. Okay, conductions are between two objects like substances which are adjacent, okay, to each other. Convection involves some part of conductions and fluid motions. Radiation is the transfer of energy due to emissions of electromagnetic waves. And the more details you can look at, you can go through the text. It's not going to be part of the course though. Okay, so with that, I'm going to end the lecture, and the next lecture we are going to talk about the work, okay, including electrical work and several form of work.